The James Webb Space Telescope has just discovered galaxies older than time. Let that sink in for a moment. Galaxies that, according to our best theories, should not exist. Galaxies that formed so early in the universe's history that there simply was not enough time to build them. And yet, there they are, massive, bright, and impossibly ancient. This is not speculation. This is not science fiction. This is what Webb is showing us right now, image after image, observation after observation, and it is forcing astronomers to ask questions they never thought they would have to answer. Something extraordinary is happening in astronomy. In just the past year, the James Webb Space Telescope has shattered records, challenged assumptions, and uncovered a universe far stranger than anyone predicted. It has captured galaxies caught in gravitational dances. It has detected organic molecules in places where chemistry should barely exist. It has observed a planet with an atmosphere that defies every known rule. And most troubling of all, it has revealed massive galaxies forming in the universe's first few hundred million years. Galaxies that simply should not be there. If you enjoy calm, careful explorations of ideas like this, you might want to like the video and subscribe. It helps the channel continue moving forward. This is not just about beautiful images or distant objects with complicated names. These discoveries are forcing scientists to confront uncomfortable possibilities. Are our models of the universe incomplete? Did galaxies, planets, and even chemistry itself emerge differently than we believed? And are we finally seeing evidence that the universe's earliest chapters were far more complex, far more dynamic than the story we have been telling for decades? Tonight, you are about to see how Webb's latest observations, from nearby dwarf galaxies to the very edge of cosmic time, are reshaping our understanding of reality itself. Because the universe Webb is revealing does not behave the way our theories predicted, and that changes everything. Let us begin at the beginning, or rather, as close to the beginning as human technology has ever allowed us to see. Part 1. How we see the past. To understand why Webb's discoveries are so troubling, we first need to understand how we look back in time. When you look at a star in the night sky, you are not seeing it as it is right now. You are seeing it as it was years, decades, or even centuries ago. Because light, despite being the fastest thing in the universe, still takes time to travel. The light from our sun takes 8 minutes to reach Earth. The light from the nearest star system, Alpha Centauri, takes more than 4 years. And the light from distant galaxies takes billions of years to arrive. This makes astronomy unique among the sciences. We do not study the universe as it is, we study its history. Every observation is a window into the past. The farther we look, the deeper into cosmic history we peer. But there is a catch. The universe is not static, it is expanding. And as space itself stretches, it stretches the light traveling through it. This phenomenon is called cosmological redshift. As a photon journeys across billions of light years, its wavelength gets pulled longer and longer, shifting toward the red end of the electromagnetic spectrum. The more the universe expands during the light's journey, the more extreme the redshift becomes. Astronomers use redshift as a cosmic clock. A redshift of 0 means an object is nearby, practically in our cosmic neighborhood. A redshift of 1 corresponds to a galaxy we see as it was about 8 billion years ago. A redshift of 6 means a galaxy from when the universe was less than 1 billion years old. The higher the redshift, the farther back in time we are looking. For decades, the Hubble Space Telescope was our primary window into the deep universe. Hubble transformed astronomy. It revealed galaxies by the thousands, captured the cosmos in unprecedented detail, and pushed our view back to within a few 100 million years of the Big Bang itself. One of its most distant discoveries was a galaxy known as GN-Z11, seen as it existed just 400 million years after the universe began. Its redshift was about 11. For a long time, Astronomers believed that objects beyond this threshold were extraordinarily rare. The early universe, they thought, was a sparse and quiet place. Galaxies were only just beginning to flicker into existence, small, faint, and scattered thinly across the cosmic dawn. But Hubble had a limitation. It was designed primarily to observe visible and ultraviolet light, with only modest infrared capabilities. And the light from the earliest galaxies, stretched by billions of years of cosmic expansion, arrives at Earth almost entirely in the infrared part of the spectrum. Hubble could see hints of these distant objects, but it was working at the very edge of its abilities. Then came Webb. The James Webb Space Telescope was built specifically for this task. Its instruments are optimized to detect faint infrared light from the most distant corners of space and time. Its mirror, nearly 7 meters across, can gather far more light than Hubble's. Its sensors are cooled to near absolute zero, allowing them to detect the faintest thermal whispers from ancient galaxies. Webb was designed from the beginning to peer into the universe's infancy and see what Hubble could only glimpse. And when Webb turned its gaze toward the early cosmos, what it found was shocking. The empty, quiet, early universe scientists expected simply was not there. Instead, Webb found galaxies everywhere. Not scattered, isolated objects struggling to form, but dozens, then hundreds of galaxies at redshifts higher than anything Hubble had ever reliably detected. Galaxies at redshift 11, redshift 12, redshift 13, and even beyond. Some appeared to have formed just 200 to 300 million years after the Big Bang. One candidate, known as Glass-Z13, existed roughly 300 million years after the universe began, pushing back the boundaries of observable cosmic history. But here's the problem. It was not just that these galaxies were early, it was that they were abundant. They were not anomalies, they were common. And according to the standard cosmological model, the framework that has guided astronomy for decades, there should not have been enough time for so many galaxies to form, let alone grow large and bright. Yet Webb was seeing them, already mature, already shining. And that was only the beginning of the problem. Part 2. The Impossible Galaxies. As astronomers began analyzing Webb's data more carefully, they realized the situation was far worse than they initially thought. It was not just that galaxies existed earlier than expected, it was that some of them were massive, shockingly, impossibly massive. We are talking about galaxies rivaling or even exceeding the Milky Way in stellar content, appearing less than 1 billion years after the Big Bang. To understand why this is such a problem, you need to understand how galaxies are supposed to form. According to the standard cosmological model, galaxies do not simply appear out of nowhere. They grow gradually, over hundreds of millions of years, inside vast structures of dark matter known as halos. Dark matter, the invisible substance that makes up about 85% of all matter in the universe, acts as gravitational scaffolding. It clumps together first, creating wells of gravity that attract normal matter. Gas falls into these wells, cools, condenses, and eventually forms stars. Over time, as more matter accumulates, small galaxies merge into larger ones. It is a slow, hierarchical process. In the early universe, this process should be even slower. There is less time for matter to clump. Dark matter halos are smaller, less developed. The first galaxies should be tiny, dwarf systems with relatively few stars. Nothing like the grand spiral and elliptical galaxies we see today. That is the theory. But Webb's observations tell a very different story. Some of the galaxies Webb has detected in the first billion years of cosmic history contain stellar masses comparable to the Milky Way, a galaxy that took more than 13 billion years to build. One galaxy candidate observed by Webb appears to have a stellar mass exceeding 100 billion times the mass of the Sun, despite forming when the universe was less than 700 million years old. Another massive structure appeared at a redshift of around 10, corresponding to just 480 million years after the Big Bang. These are not just slightly ahead of schedule, they are impossibly ahead of schedule. Under current models, the dark matter halos required to accumulate that much matter and form that many stars simply did not exist yet. The universe had not had enough time to build the gravitational foundations these galaxies would need. It is like finding a fully constructed skyscraper on a plot of land where the foundation was poured yesterday. Astronomer Claudia Lagos put it bluntly, "The presence of such massive galaxies so early in cosmic history poses a serious challenge to the standard cosmological framework. The universe, as we understand it, simply did not have enough time to assemble them." And it is not just one or two outliers. Webb keeps finding these objects, image after image, survey after survey, massive luminous galaxies appearing in an era when they should not exist. Some researchers initially wondered if the observations might be misleading. Perhaps these were not galaxies at all, but something else, supermassive black holes, for example, whose brilliant emission could mimic a galaxy's light. But follow-up spectroscopy confirmed it. These are real galaxies, packed with stars, shining from the cosmic dawn. Others suggested that maybe we were misinterpreting the redshifts, that these objects were not as distant as they appear. But the measurements held up. The redshifts are real. These galaxies really are that old. So if the observations are correct and the galaxies are real, then something is wrong with our understanding. Either galaxies formed much faster than we thought possible, or dark matter behaves differently in the early universe than our models predict, or there is something fundamental missing from our cosmological framework altogether. This is where the cracks in modern cosmology begin to show, because Webb's discoveries are not just challenging minor details or adjusting timelines by a few million years, they are questioning the foundation, the very scaffolding upon which our understanding of cosmic history is built. But the story does not end with distant galaxies. While Webb was rewriting the rules of the early universe, it was also transforming our view of galaxies much closer to home, and what it found there was equally surprising. Part 3. The Chemistry of the Early Cosmos. While massive ancient galaxies were breaking cosmological models, Webb was also revealing something unexpected in smaller, nearby systems, something that challenges our understanding of how complex chemistry emerges in the universe. In one striking observation, Webb captured two dwarf galaxies locked in a slow gravitational embrace. These galaxies are tiny compared to giants like the Milky Way or Andromeda, but what Webb revealed in this image was remarkable. Intricate structure, bursts of intense star formation, delicate streams of gas and dust being pulled and shaped by their mutual gravity, a cosmic dance playing out over millions of years. This was not just a beautiful picture. It was a window into a fundamental process. Galaxies are not static islands floating in the void. They interact, they collide, they exchange material. They trigger waves of star formation in one another. And these encounters, these mergers and near misses, may have been far more common in the early universe than we ever imagined. In the dense, crowded cosmos of the first billion years, galaxies were constantly bumping into each other, stirring up gas, igniting stars, and growing through violent interactions. This helps explain, at least in part, how some galaxies may have grown so massive so quickly. But it also raises another question. If galaxies were forming and merging this actively in the early universe, what about the chemistry? What about the elements needed to build planets, atmospheres, and eventually, life itself? That question led to one of Webb's most surprising discoveries. Webb turned its gaze toward a nearby dwarf galaxy known as Sextans A. This small metal-poor system is thought to resemble the primitive galaxies of the early universe, systems with very few heavy elements, where stars are made almost entirely of hydrogen and helium. In such an environment, complex chemistry should struggle to take hold. Heavy elements like carbon, oxygen, and nitrogen, the building blocks of organic molecules, are forged inside stars and scattered into space when those stars die. In a young, metal-poor galaxy, there simply are not many of these elements available yet. Or so we thought. When Webb analyzed the light from Sextans A, it detected something unexpected: polycyclic aromatic hydrocarbons. Carbon-based molecules, rings of carbon and hydrogen atoms linked together in complex structures. They are organic compounds, the same family of molecules found in soot, coal, and even in the dust between stars in our own galaxy. They are considered some of the fundamental building blocks of complex chemistry in space. And Webb found them in an environment where they should not exist. Sextans A is extremely poor in heavy elements, far poorer than the Milky Way. According to our models, such conditions should make it nearly impossible for complex organic molecules to form. There simply is not enough carbon, not enough raw material. And yet, there they were. Dust, organic molecules, chemical complexity emerging in a harsh, primitive environment. This discovery has profound implications. It suggests that the ingredients for stars, planets, and possibly even life may have emerged much sooner in cosmic history than we ever thought. If complex organic chemistry can appear in metal-poor galaxies like Sextans A, then it could have appeared in the early universe as well. Perhaps within the first billion years. Perhaps inside those same massive galaxies Webb has been discovering. Think about what that means. We have always assumed that life, or at least the chemistry that leads to life, requires a certain level of cosmic maturity. Stars must live and die, scattering heavy elements into space. Subsequent generations of stars form from that enriched material, building planets with the elements necessary for complex chemistry. This process takes time, billions of years. But if Webb is right, that timeline may be wrong. Chemistry might not need billions of years to get started. It may have begun far earlier, under far harsher conditions, in a universe we thought was still too young and too simple. And just as this realization was sinking in, Webb found something even stranger, something that does not just challenge our models of chemistry, but our entire understanding of how planets form and survive. Part 4. The planet that shouldn't exist. While Webb was rewriting the rules for galaxies and chemistry, it stumbled upon something in our own cosmic neighborhood that defies every model of planetary science we have: an exoplanet orbiting a pulsar. Now, pulsars are not normal stars. They're not even living stars. A pulsar is the crushed remnant of a massive star that exploded in a supernova. It is a sphere of neutron-degenerate matter roughly the size of a city, yet containing more mass than our Sun. It spins at incredible speeds, sometimes hundreds of times per second, blasting jets of radiation into space like a cosmic lighthouse. The environment around a pulsar is one of the most extreme places in the universe. Intense magnetic fields, torrents of high-energy particles, radiation that would sterilize anything in its vicinity. The fact that a planet exists around such an object is already surprising. Planets typically form in disks of gas and dust around young stars. But when a massive star goes supernova, it obliterates everything nearby. Any planets that existed before the explosion should have been vaporized or flung into interstellar space. So how does a planet end up orbiting a pulsar? There are theories. Maybe the planet formed after the supernova from the debris disk left behind. Maybe it was captured later, a rogue world that wandered too close and became trapped by the pulsar's gravity. Maybe it is the core of a former gas giant, stripped of its outer layers by the blast. Nobody knows for certain. But here is where it gets truly bizarre. When Webb studied this planet, it detected an atmosphere. And not just any atmosphere, an atmosphere dominated by molecules that should not be there. Its composition is unlike anything we have observed before. It does not match the atmospheres of rocky planets like Earth or Venus. It does not match gas giants like Jupiter or Saturn. It does not match ice giants like Neptune. It is something entirely different. The details are still being analyzed, but the preliminary data suggests a chemical mixture that current models of atmospheric formation and evolution simply cannot explain. How did this atmosphere form? How has it survived in such a hostile environment? The radiation from the pulsar should be stripping it away, molecule by molecule, and yet it is still there. This discovery raises uncomfortable questions. If a planet can survive around a pulsar, and not just survive but retain a complex atmosphere, then what else have we been wrong about? How many other extreme environments might harbor worlds we have dismissed as impossible? Planetary science, like cosmology, is built on models. Models of how planets form, how they evolve, what kinds of atmospheres they can sustain, and where we should look for them. But Webb's pulsar planet does not fit any of those models. It exists in a category we did not know existed. It is breaking rules we thought were fundamental. And this is becoming a pattern. Webb is not just filling gaps in our knowledge, it is exposing gaps in our understanding. Over and over again, it is finding objects that should not be there, in places they should not exist, with properties they should not have. Which brings us to perhaps the strangest discovery of all. An object so unusual, so difficult to classify, that astronomers have started calling it astronomy's platypus. Part 5. Astronomy's platypus. While searching through Webb's deep field images, astronomers using the MIRI instrument, Webb's mid-infrared instrument, detected something extraordinary. An object so red, so faint, and so unusual that previous telescopes had completely missed it. At first glance, it seemed unremarkable, just another red dot in a sea of distant galaxies. But as researchers began analyzing its properties, nothing made sense. It was not moving like a nearby star, it was not behaving like a dusty galaxy. It did not fit any known classification. Every attempt to categorize it failed. The object's color was the first clue that something was wrong. It appeared extremely red in infrared wavelengths, far redder than typical galaxies at any distance. This kind of extreme redness usually points to one of two explanations. Either the object is heavily obscured by dust, or it is extraordinarily distant, with its light stretched by billions of years of cosmic expansion. Researchers considered the first possibility. Perhaps it was simply a dusty galaxy relatively nearby, its light reddened by thick clouds of interstellar material. But the data did not support that interpretation. The amount of dust required would be unrealistic. The object's spectral signature did not match known dusty galaxies. So they turned to the second possibility. Maybe it was a heavily obscured galaxy from a later cosmic era, a few billion years after the Big Bang, caught in an especially dusty phase of evolution. But that explanation also fell apart under closer scrutiny. The object was too compact, too luminous, and its properties did not align with galaxies from that epoch either. Then came the most dramatic possibility. What if this object belonged to an entirely new class of galaxies? A type of galaxy we had never seen before. Compact, intensely luminous, and unlike anything in our cosmic senses. As more observations accumulated, this interpretation began to look increasingly likely. And then, similar objects started appearing in other Webb surveys. Compact red sources that defied easy classification. objects that did not fit into the neat categories astronomers had spent decades constructing. They were so strange, so unlike anything expected, that researchers began calling them astronomy's platypus, after the bizarre animal that baffled scientists when it was first discovered because it seemed to combine features of mammals, birds, and reptiles all at once. But here is where the implications become staggering. If the most compelling interpretation is correct, this object's redshift could be around 15, possibly even higher. That would place it roughly 100 million years after the Big Bang. Not 300 million, not 200 million, 100 million years. That would make it the most distant and earliest galaxy ever observed. It would push us into an era of cosmic history we have barely begun to explore. And if that redshift is accurate, the object's properties become even more troubling. At a redshift of about 15, this galaxy would have formed when the universe was only about 1% of its current age. According to the standard cosmological model, the universe at that time should have been relatively simple. Dark matter halos would still be small, only just beginning to collapse. The first stars might have only just started to ignite. Large-scale structures, galaxies, clusters, the cosmic web should still be in their earliest, most primitive stages. But this object is not primitive. It is compact, yes, but it is also remarkably bright. Its luminosity suggests it contains a substantial number of stars, possibly billions of them, already assembled into a coherent structure. The amount of mass implied by its brightness is staggering for such an early time. This is the same problem seen with the massive galaxies earlier, only taken to an even more extreme level. If this object truly formed at such an early epoch, then the universe had even less time to build it. Under current cosmology, there simply was not enough time. Not enough time for dark matter halos to grow large enough. Not enough time for gas to cool and collapse efficiently enough. Not enough time for stars to form rapidly enough to create something like this. The universe was too young. The necessary structures did not yet exist. And yet, Webb keeps finding them. These compact red galaxies, these so-called platypuses of astronomy, are now appearing in multiple surveys. They are not flukes. They are not measurement errors. They are real objects, detected repeatedly with consistent properties. Some of them appear to contain more stellar mass than the Milky Way, despite forming within the universe's first few 100 million years. This directly challenges one of the core principles of modern cosmology. The idea that dark matter halos are the slow-building scaffolding required for galaxy formation. If galaxies like this can form so early and so quickly, then either dark matter behaves very differently in the early universe than we thought, or something else is happening, something our models do not account for. Astronomers are now being forced to ask questions that would have sounded absurd just a few years ago. Did galaxies form faster than we believed possible? Is there a mechanism for rapid collapse and star formation that we have overlooked? Does dark matter interact with itself or with normal matter in ways we do not yet understand? Or is the problem even deeper? Something wrong with our understanding of the Big Bang itself, the expansion of the universe, or the timeline of cosmic history? These are not small questions. These are foundational questions, and Webb's observations are forcing the scientific community to confront them. Because if these compact red galaxies are real, and the evidence strongly suggests they are, then the story we have been telling about the universe's first few 100 million years is incomplete at best and fundamentally wrong at worst. Part 6. The Crisis in Cosmology. Let us step back for a moment and look at what Webb has revealed so far. Galaxies forming just 200 to 300 million years after the Big Bang. Massive galaxies, rivaling the Milky Way in size, appearing less than 1 billion years into cosmic history. Complex organic chemistry emerging in environments too harsh and too metal-poor to support it. A planet with an inexplicable atmosphere orbiting a dead star, and compact, luminous galaxies at the very edge of observable time, objects so strange they do not fit into any existing category. Taken individually, each of these discoveries is remarkable. Together, they represent something more serious, a pattern of observations that our current cosmological framework struggles to explain. This is not a matter of tweaking a few parameters or adjusting some minor details. The discrepancies are too large, too consistent, and too fundamental. As astronomer Claudia Lagos noted, the presence of such massive galaxies so early in cosmic history poses a serious challenge to our understanding. The universe, as we have modeled it for decades, simply did not have enough time to build them. So what went wrong? Or more accurately, what are we missing? Scientists are exploring several possibilities, and not all of them are comfortable. The first option is that galaxies formed much more efficiently than we thought. Perhaps star formation in the early universe was not slow and gradual, but explosive and rapid. Maybe gas collapsed faster, stars ignited more quickly, and galaxies assembled in sudden bursts rather than steady accumulation. This would require rethinking our models of star formation, but it would not necessarily break the underlying cosmology. It would just mean the process was more violent and chaotic than we assumed. The second option is that dark matter behaves differently than our models predict. Maybe dark matter particles interact with each other in ways we have not accounted for. Maybe they clump more efficiently in the early universe, creating larger halos faster than the standard cold dark matter model allows. This would be a significant revision, but still within the realm of known physics. But then there are more radical possibilities. Some researchers are revisiting ideas that were once considered fringe. Cyclic cosmology, for instance, the notion that our universe is just one phase in an endless series of expansions and contractions. Nobel Prize-winning physicist Roger Penrose has proposed a model in which the universe undergoes infinite cycles, each one emerging from the remnants of the previous one. In such a framework, the Big Bang is not the absolute beginning, but a transition point. And structures we see in the early universe might not have formed from scratch. They might be echoes, inheritances from a previous cosmic cycle. Then there is the multiverse, not as science fiction, but as a serious theoretical framework. If our universe is one of many, each with slightly different physical laws, different constants, different initial conditions, then perhaps the structures Webb is seeing are the result of conditions we simply do not have in our equations. Maybe we live in a universe where galaxy formation happens faster, dark matter behaves unusually, or the early expansion was different than the models assume. Some physicists have even begun questioning whether the Big Bang itself happened the way we think it did. What if the universe did not emerge from a singular point of infinite density? What if it transitioned from a previous state, a collapsing universe, a quantum fluctuation, or something else entirely? These ideas sound radical, but they are being discussed in serious academic circles now because Webb's data refuses to fit neatly into the old assumptions. None of these ideas are proven, many of them are speculative, but the fact that they are being taken seriously tells you something important. The standard model is under strain. The observations do not match the predictions, and when observations and theory diverge this dramatically, something has to give. Here is what we know for certain. The early universe was not the simple, quiet place we thought it was. It was dynamic, it was crowded, it was chemically rich, it was astonishingly productive. Galaxies did not trickle into existence slowly over billions of years. They burst into being rapidly, in vast numbers, with sizes and complexities we did not think were possible so soon. And this means our story of cosmic history, the narrative that has guided astronomy for generations, needs revision. That does not mean everything we know is wrong. The Big Bang still happened, the universe is still expanding, dark matter still exists. The evidence for these things is overwhelming. But the details, the timeline, the mechanisms, the processes by which structure emerged, those details are now in question. And those details matter, because they shape our understanding of where we came from, how galaxies like ours formed, and ultimately, how rare or common planets, chemistry, and life might be in the cosmos. Webb has not solved these mysteries. It has deepened them. Every answer it provides seems to raise 3 new questions, and that, in a way, is exactly what great science is supposed to do. So, where does this leave us? The James Webb Space Telescope has been operational for just over 2 years. 2 years! And in that time, it has fundamentally altered our view of the universe. It has pushed the boundaries of observable cosmic history back to within 100 million years of the Big Bang. It has revealed a cosmos far more complex, far more active, and far more mysterious than we ever anticipated. But here's the important part. Webb's mission is far from over. Every week, new data arrives, new images are processed, new spectra are analyzed. And with each observation, there's the potential for another breakthrough, or another mystery. Astronomers are already planning deeper surveys, targeting even earlier epochs, searching for the very first galaxies to ignite in the primordial darkness. They're looking for the signatures of the first stars, the formation of the first black holes, and the chemical enrichment that would eventually make planets and life possible. And they're waiting to see if the patterns Webb has uncovered will hold, or if the universe has even stranger surprises waiting in the data yet to come. What's becoming clear is this. The universe's early years were not a slow, quiet awakening. They were explosive, chaotic, and astonishingly fertile. Galaxies didn't take billions of years to get started. They hit the ground running. Chemistry didn't wait for cosmic maturity. It began almost immediately, in harsh environments where it had no right to exist. And the structures we see today, the galaxies, the stars, the planets, perhaps even the building blocks of life, may have much older, much stranger origins than we ever imagined. This is what makes Webb's discoveries so profound. They're not just expanding our knowledge, they're forcing us to rethink the foundations. They're challenging assumptions we've held for decades and opening doors to possibilities we hadn't seriously considered. Some of those possibilities are incremental, adjustments to star formation models, refinements to dark matter theory. Others are radical, cyclic universes, multiverses, entirely new physics operating in the early cosmos. We don't know yet which direction the answers will take us, but that uncertainty, that tension between what we observe and what we understand is where science lives. It's where progress happens. Because the universe doesn't care about our theories. It doesn't conform to our expectations. It simply is. And our job, as scientists, as explorers, as curious beings trying to understand our place in the cosmos, is to look honestly at what the universe shows us, even when it contradicts everything we thought we knew. Webb is doing that. Image by image, spectrum by spectrum, discovery by discovery, it's revealing a universe stranger and more wondrous than the one we imagined. And we are privileged to be here, right now, watching this story unfold in real time. The universe is being rewritten, and this is only the beginning. Thank you for taking this journey through galaxies, time, and the limits of our understanding. If this story made you pause, if it shifted how you see the cosmos even slightly, let me know in the comments. Do you think we're on the verge of a major cosmological revolution? Or will these mysteries eventually fold back into the standard model with a few adjustments? What discovery from Webb surprised you most? If this video helped you think, the best way to support the channel is a like. Subscribe if you want to keep exploring where observation meets uncertainty, where data challenges theory, and where the universe refuses to play by our rules. The cosmos is not obligated to make sense to us, but it rewards those willing to look carefully, question deeply, and accept that the answers may be stranger than we hoped. See you in the next one.